Good morning, dear student. In previous lecture, we already discussed the type first of the ferrites based on the crystal structure, that is spinel ferrites. So in today's lecture, we are very much interested in the second ferrites, that is garnets. So we will discuss the garnets and hexagonal ferrites in this lecture. So what is this garnets? These garnets having general formula R3 Fe5O12. So this garnets having general formula R3 Fe5O12. So this R is your rare earth trivalent cation, rare earth trivalent cation, or yttrium cation, yttrium cation. So you should keep in mind the general formula, that is in normal spin. So we already discussed the spinel, that it having a formula, that is Ab2 for general formula. So garnets, that is R3Fe5O12, where R is your rare earth trivalent cation or yttrium cation. The second point regarding to this garnet is that the fundamental crystal structure, the fundamental crystal structure the fundamental crystal structure is derived the fundamental crystal structure is derived from garnet minerals. Garnet mineral, it is not mineral, garnet mineral such as Mn3Al2 Si3O12. So whatever the general formula, it is derived, the fundamental crystal structure is derived from the garnet mineral, that is Mn3Al2 Si3O12, in which silica and manganese can be substituted. Silica and manganese can be substituted by yttrium and aluminium to form Y3, that is yttrium thrice Al5O12. So they have general formula R3Fe5O12, in which R is your rare earth trivalent cation or yttrium cation, and the structure is derived from the garnet minerals, that is Mn3Al2 Si3O12, in which silica and manganese can be substituted by yttrium and aluminium to form Y3Al5O12. If you consider the next important points regarding to this garnet is that for magnetic material, the third point is that for magnetic garnet, aluminium further replace by Fe. So for magnetic garnet, aluminium is further replaced by Fe. So at least you should know these 2-3 points regarding to these garnets. Keep in mind the general formula, that is R3Fe5O12. Then what is R? It is your trivalent cation or yttrium cation, and the crystal structure is derived from the minerals, that is Mn3Al2 Si3O12, in which silica and manganese can be replaced by yttrium and aluminium to form Y3Al5O12. And for magnetic materials, for magnetic garnet, aluminium is further replaced by Fe. So this is all about garnet. Let us discuss some important points regarding to the hexagonal ferrites. What is this hexagonal ferrites? The third types of ferrites based on the crystal structure, that is hexagonal ferrites. What is this hexagonal ferrites? So the first point is that these hexagonal ferrites are the family. These ferrites, these ferrites of these ferrites are a family of interrelated interrelated compounds, interrelated compounds with hexagonal and rhombohedral symmetry, and rhombohedral symmetry rhombohedral symmetry. So these ferrites are a family of interrelated compounds with hexagonal and rhombohedral symmetries. Second, the composition, that is, if you consider the composition of these hexagonal ferrites, that is, uh, these are the combination. If you consider the composition, these ferrites, hexagonal ferrites, are the combination of MEO, Fe2O3, and barium oxide, where this Me is your divalent cation, that is, it is present in plus 2 oxidation state, divalent cation. Okay, so these ferrites, they are the interrelated compound with hexagonal or rhombohedral symmetry. The composition, the combination of three oxides, that is MU, iron oxide, and barium oxide, in which Me is divalent cation. And then if you consider all the related compounds can be understand, so whatever the compounds of these hexagonal ferrites ba- can be understand as a stacking of three basic blocks. So whatever the compounds of these hexagonal ferrites can be understood as a stacking of three basic blocks, that is S, then R, and then T. So what is these blocks? So S, it is formed by two formula unit. So S block, it is not the periodic elements. It is not the symbol for S block element. So all the related compound can be understand by stacking of three basic blocks. So three basic units, that is, it is denoted by symbol capital S, R, and T. So this first block or this first unit is made up of by two formula unit, two formula unit, that is Me, Fe2, Me, Fe2O4, Me, Fe2O4, Me, Fe2O4. Second, that is R unit, it having barium, Fe6O11, having -2 charge, and the third one, that is four layer with formula. So the T unit having four layer with formula, that is Ba2 Fe8O40. And again, if you consider the important points regarding to this hexagonal ferrite, is that more than one type of crystal structure is there for this hexagonal ferrites. More than one type of crystal structure is there. More than one type of crystal structure is there. More than one type of crystal structure is there for this hexagonal ferrites. So this is all about the classification on the based on the crystal structure, that is spinel ferrites, garnets, and hexagonal ferrites. At least you should know the general formula and the composition regarding to this. So generally the spinel ferrites are most common because they having a very much they having more magnetic properties. So they're having more applications as compared to these garnets and hexagonal ferrites. So at least you should know these names and their general formulas, their composition. So the next point is that we discussed, that is the two types of ferrites. That is, it is not based on the classification, that is, it is not based on the crystal structure, it is based on their properties of this magnetic material. That is, one is hard ferrites and second is soft ferrites. So what is the difference between these hard ferrites and soft ferrites? These high ferrites, if you consider the first point, that is the high ferrites having high corrosivity. High corrosivity. So what is the meaning of this? It having high corrosivity means it is difficult to demagnetize. Difficult to demagnetize. These hard ferrites having high corrosivity, and the second is what? It is difficult to demagnetize. They can be used, so they're having lots of application. It is used in manufacturing of permanent magnets. Used in manufacturing of permanent magnet. Use in manufacturing of permanent magnet for application such as refrigerator magnets, refrigerator magnets then loudspeaker and electric motors. Also, the instrument, that is NMR magnets, is also made up by this hard ferrites material. So these are the three important points. That is, the hard ferrites having high corrosivity, are difficult to demagnetize, and used in manufacturing of permanent magnets. They having different applications, that is used in refrigerator magnets, loudspeaker, electric motors, and whatever the magnets in NMR instrument, it is also made up by the hard ferrites. So let us discuss some points regarding to these soft ferrites. Soft ferrites. Soft ferrites. So they're having low corrosivity. They're having low corrosivity. They're having low corrosivity. Second, it is easy to demagnetize. Easy to demagnetize. And the third one, it is used in electronic industry. Used in electronic industry to make efficient magnet, to make efficient magnetic core. It is used in electronic industry to make efficient magnetic core called ferrite core. Called ferrite core. Called ferrite core for high frequency. Ferrite core for high frequency. Called ferrite core for high frequency inductor transformer. High frequency inductor transformer and various microwave component and various microwave components. So they're having low corrosivity, easy to demagnetize, and it is used in electronic industry to make efficient magnetic core called ferrite core for high frequency inductor, transformer, and various microwave components. So this is all about ferrites in these magnetic materials. In the next lecture, we discuss the remaining points regarding to these magnetic materials. Thank you.